Namaste. We will be building on the ideas of linear algebra through geometry, which you have already gone through many lectures. My focus of this lecture will be on what is called singular value decomposition. It is more commonly known as SVD. We will look at initially the motivation for something for SVD. Okay. Why is it that we need this idea? Historically, it was a very challenging problem to do what we are going to show here. There have been many attempts trying to get to this, but the root of it is building on the familiar Ax equal to lambda x, which is a eigenvalue eigenvector problem. It also has an interesting link in the sense that it also looks at problem of solving Ax equal to b, which is the classical systems of linear equation. To cut short some of this, many of you would have gone through the fact that if A is m cross m full rank, then solution is x is A inverse b. This is purely an algebra. So, it is purely an algebraic way of doing it, even though the focus would perhaps be on given A, find A inverse. This is a bad problem in the sense matrix inversion is not an easy problem. Numerical, it is very challenging, and if the size is very large, which is very common these days, it is almost a nightmare. But nevertheless, because a large amount of problems are modeled as Ax equal to b today, the reason being that people have tremendous options for computation, everybody attempts to model problems as Ax equal to b, and almost all solutions eventually will be how to find A inverse. And there are various numerical techniques for that, and that is a diversion from this in the sense that you do have specific subjects like computational linear algebra and numerical techniques for matrix inversion. We will not get into that. We will focus on these two connections. There are some interesting connections between them, and it will also tell us why this SVD is an indispensable tool today to look at solving problems of engineering and economics and wide diverse fields, including medical field, population dynamics, economics, so many issues, space, all these applications. Okay. Yeah. So, when we look back, we were very comfortable with the following: solving Ax equal to b, where A is a m cross m matrix, full rank. But what is realistic? When I say realistic, what you really find in almost all practical engineering and physics and economics problems, the realistic situation is solve Ax equal to B, where A is m cross n. Convenience, you can use real matrix, and most importantly m is not equal to n. So, you are looking at non-square matrices, and non-square matrices are more common than square matrices. Square matrices are convenient and nice to understand to get going. It also gives you a lot of interesting ideas, but in reality very rarely you find practical problems which start off as square matrices. And you have two cases where m is greater than n, which means you have more rows than column. And these are called tall matrices. And the other case is m is less than n, these are fat matrices. This has more columns than rows. Now, I keep saying that this is very practical. I keep saying it's very practical, and we have to justify why this is so practical. You look at tall matrices, tall cases. Typically, many of you would have done this problem, which is fairly universal problem. You have an input x of n, you get an output y of n. I am choosing discrete. This is an impulse response h of n, which is almost all problems of linear systems. Now, if you try solving this problem, you will come across this solution, y is equal to h times x, where you will have output like y1 some yk, you will have a matrix H matrix which is tall, and an input x1 to xm. Okay. So, this will be some h naught, h1, etc., etc., etc. Okay. So, it is k cross m and k is greater than m. Okay. So, almost all linear convolution systems which encompass wide variety of problems in signal processing, control, communication, and many other systems which governed by convolution. So, typically sources of such problems are typically differential equations. So, systems modeled and governed by differential equations, and at least in the discrete form you can put it in this matrix. Okay. Now, classical problem will be to solve for x, which is in some sense h inverse y. Now, we have problem because h is not square, okay, and in many cases it may not be full rank also, even that is minimum of rows or commons. What about the fat matrices? The fat matrices also come in cases typically the sources are problems which come from process control. So, you look at process control and metallurgy type of problems, metallurgical processing problems, where you get a fat matrix like equivalent of H. This also means you have to invert to solve. Again I repeat, this is very realistic and therefore very important very important because it is very realistic, and whatever domain you do, you either get a fat matrix or a tall matrix or a fat matrix which needs solutions, which is typically equivalent of inversion. Okay. Inverting square matrices, even if they are full rank, is a bad problem. When I say bad problem, numerically or even analytically a bad problem. If size is large, typically greater than 100 cross 100, which is very common these days, it is much worse. Now we have this problem of tall or fat matrices, large size. So typically 1000 cross 100 is not uncommon, it is very common to find such size matrices, and inverting it is almost a nightmare. Yet it has to be done. So this is the interesting point where modern linear algebra, one dominant aspect of modern linear algebra, which is the SVD. This is where the role of SVD comes in. So we will try to understand what SVD is. Initially we will do it purely algebraic. In 5 minutes it is done. You get the answer, but you probably have no idea what is going on inside and why it works, and if it does not work well, what to do, and if you want to do it all over from scratch, what is it that all this information is missing when you look at purely algebraic approach. But the first part I will do the algebraic part in few minutes, so that you are convinced that yes, it works and this is the way it is, and in the subsequent progress of lectures we will look at the geometric approach, which is really the crux of the issue, and also probably the most elegant part of linear algebra through geometry is captured in that. Okay, so let us get back. What is our problem now? What is our problem now? Solve system of equation of the type Ax equal to B, call it equation 1, where A is m cross n, m greater than n, and I will assume A is real matrix. Okay. Since A is not square, we cannot define the kind of inverse which we have been familiar with, but we have to do what we already know and build a little on it. This is the way most of the interesting things happen, where you incrementally get the next idea, and when you actually end up solving, you probably understand the previous idea much better, and you probably reinterpret the previous idea in a more elegant way, which perhaps you might have missed. Okay, so I will treat this purely as an algebra problem. And what is algebra problem? Mostly symbol manipulation. Algebra is very useful because you can manipulate symbols very easily. All manipulation of symbols need not give you meaning, but those symbols which you can manipulate probably give you the answer you are looking for, and then after the answer is acceptable, you probably dig deep and figure out why the answer is correct, what makes it correct, so on and so forth. Okay? Yeah. So for the equation 1, we want to solve Ax equal to B. If it was by chance, if it was square, I would have got X is A inverse B. Okay. This we keep it in mind. So, basically I want a solution which looks like this. Okay. It need not be exactly like this, but it should look like this, then I know very well that for some interesting conditions that this matches everything that I have been doing. Okay. Now, you pre-multiply both sides by A transpose. So, I get an equation now, A transpose A times X is A transpose B. So, this is equation 2. So, already it is little different. Now, I focus on A transpose A. So, what does A transpose A look like? Given A, which is a real matrix, A transpose A is real symmetric matrix. What is the size of A transpose A? A was M cross N, this will be N cross M, therefore, you now have N cross N. N cross N square. So, somehow I have been able to get a square matrix times X is not B, but some cousin of B, just like A transpose A is some cousin of A. So, we now try to look at A transpose A times X is A transpose B, which this looks like some B cap, and this if you want you can put it as A cap. So, A cap X equal to B cap 3A. So, I am now trying to solve a problem like this, and this is square. Therefore, if everything goes well, we will see that X cap is simply A cap inverse B cap. Now, if I plug this in, X cap will simply be A cap inverse, which is A transpose A inverse, B cap is A transpose B. If I want to reduce this, I can even look at this as A dagger B. This A dagger is simply the A transpose A inverse A transpose. So, instead of solving Ax equal to B, where A is given, look for X which has to match B, I now get a X cap which is not the same as X, because B cap is not the same as B. So, what is the relationship between the original X and the X cap and the original B and the B cap? This is really what the solution to the non-square matrix is. This is called the generalized inverse. This notation A dagger is called generalized inverse of A. This is important because you have structured I would call it easy, in the sense it is easy on the eye, easy solution to invert a non-square matrix. So, you wanted to solve for x, you got answer, you got an answer x cap. We will look at it little in depth later, but basically this x cap minus x, if I take the 2 norm, it gives you an error which is greater than 0, which means it is not an exact solution. But approximate to x, if at all x was the solution. Okay? And this approximation is actually least squared, meaning the 2 norm of it can be minimized, or the minimum 2 norm solution, least square, which means not exact. Why it is not exact? Because Ax equal to b is inconsistent. It is either over determined or under determined. In most cases it will have infinite solutions. You pick the best, and this best is in the least squared sense. Okay, so let us capture the entire essence of it. You were trying to solve Ax equal to b, m cross n, m not equal to n. You ended up solving some a cap x cap equal to b cap, where x cap is approximately x and b cap is approximately b, not exact. But so what this means is, in the solution space of Ax equal to b, you do not have a solution, no solution for x for given a and b, but there exists an a cap and a b cap for which x cap exists and b cap is in some sense close to b, x cap is close to x. This close can be under quotes because this closeness is norm. Close means 2 norm, length, minimum length. Yeah, what did we do? We just manipulated the symbols. Instead of A inverse, we got a new inverse which was A dagger, which was by definition simply A transpose A inverse A transpose. Now, is there any other way to work? Yes, there is another way to work, where the matrix is fat. I am sure all of you can try it out. You will also end up getting A transpose, and given A, given any A, please remember A transpose A and A transpose, this is n cross n, this will be m cross n if this is m cross n. Both are square now and they are symmetric, real symmetric. So, both are square and real symmetric. And recall what you did for square matrices, real symmetric matrices. Suppose A is m cross m real symmetric matrices. I can solve for eigenvalue eigenvectors of this. Axi is lambda I xi, let us say I equal to 1 to m. Suppose these lambdas, this set lambda eigenvalues I equal to 1 to m are distinct, even if they are not distinct, the idea is extendable, are distinct, then we can find a matrix U which is made up of x1, x2, xm, which are the eigenvectors, such that U transpose AU will be a diagonal matrix where these eigenvectors are normalized. Further, not only normalized, they are orthonormalized, they are orthogonal. So, a real symmetric matrix with distinct eigenvalues is orthogonally diagonalizable. This is the result which you are already familiar with. Where did you get the matrix to diagonalize it? You got the matrix from its eigenvectors. These eigenvectors are orthogonal. I normalize it and use this, because this immediately implies there exists matrices U such that U transpose U or UU transpose is identity. These are called orthonormal matrices. Orthogonal matrices, orthonormal matrices. So, to do SVD, we use many things. What are the things we use? We use orthogonal, orthonormal vectors. We use ideas of eigenspace of real symmetric matrices. And when you say U transpose AU is D, that is starting from A, you want a diagonal representation of A. From A you extracted U, from U you made it orthonormal, then constructed U transpose and U, and you simply made this as U transpose AU is D, which is equivalent to saying U transpose DU is A. This in the reverse sense is interesting. In the reverse sense, it is saying I have factorized A to 3 components. one is U, the other is U transpose and D. So, singular value decomposition can also be seen as a matrix factorization, meaning a complex matrix, complex means not in numbers, but complex in structure, is broken up into two elegant orthonormal sectors and one very simple diagonal sector. So, basically it is like factorizing a nth degree polynomial into first and second order polynomials. It is still total, in totality it is still the nth order polynomial, but you have factorized into 1 and 2 order polynomials because you can handle it easier. This is the same problem. So, SVD is another matrix factorization which you are already familiar, you already done LU factorization, LUD, right, then QR factorization. So many factorizations are there for a given matrix A. SVD is one such factorization. Okay. Okay, so what we will recap with what we have done in this lecture. First thing, we attempted solving Ax equal to B, but for a case where A has m cross n and m is not equal to n, okay, very practical case. We did the algebraic solution by finding an equivalent inverse for tall matrices or fat matrices called generalized inverse, which took the form of A transpose A inverse A transpose. We did not solve Ax equal to B, but we solved A cap x cap equal to B cap. This was an exact solution, but B cap was not equal to B and therefore x cap is not equal to x. But what is interesting, they are close in the least square sense. This was purely algebraic. The next session we will look at the geometric way to solve this, so that there is better clarity and the beauty, the elegance. Probably the most beautiful of results in linear algebra is actually the singular value decomposition when it is put in the geometric language. We will do that. Okay. Thank you.